A period of an ideal mathematical pendulum, t, equals 3.14 seconds. If the measurement was done on the surface of the Earth, what is the period of the same pendulum on the Moon? Additionally, we know gravitational acceleration on the surface of the Earth, which is 10 meters per second square, and gravitational acceleration at the surface of the Moon, which has value of 1.6. Basically, in this question we have period and we have gravitational acceleration. We are looking for another period, a period after moving this pendulum to the surface of the Moon. Let's have a look at the formulas that we have. The first quite obvious choice is for the formula for period. That's this one. And in this formula we have omega, angular frequency, which is quite easy to calculate. The second formula that we can take into account is this one. That's the only pendulum related formula which contains gravity, gravitational acceleration. So we have these two formulas in common, that they have the angular frequency, both of them, and we also have the length of the pendulum. Actually, the question has a hint. First, find the angular frequency, and this is exactly what we can do with the formula number 1, t equals 2 pi over omega, and the length of the pendulum, and this is exactly what we can find using the second of these formulas, which says that omega equals square root of g, which is gravitational acceleration, over L, which is the length of the pendulum. So let's use the first formula and calculate omega. Omega equals 2 pi over t, over period. We know that this period is 3.14, so it's 2 pi over 3.14. Quite incidentally, after the calculation, we get 2, exactly 2 radians per second. This is the angular frequency of the pendulum. Please note that this is the pendulum measured on the Earth, so we are on the Earth at the moment. Now we can use the second formula, which says omega equals square root of g over L. To calculate, to find the remaining value here, we know omega, we know g, we are looking for L, for the length of the pendulum. To calculate, to make any use of this formula, we have to get rid of the square root, and we will do so by squaring both sides of this equation. Therefore, omega square equals g over L. And now we can find L as g over omega square. G, I remind you, we are still on Earth. G is 10 over omega square. Omega has been calculated as 2, so it's 2 square. It's 10 over 4. It's 2.5 meters. That's the length of the pendulum. At this moment, we are ready to go ahead to the second part of the solution. When we have everything known, we know the length of the pendulum, and we know the gravitational acceleration at the surface of the Moon. This means that using this length here and the gravitational acceleration on the surface of the Moon, we can calculate the angular frequency on the surface of the Moon. Having angular frequency, we can find the period on the surface of the Moon. I will draw a big line here, put the title moon. And now omega on the moon, you could use a index here to make a difference between this omega or this omega. In my opinion, it is quite enough that we have this line here which separates the calculation for the Earth and the calculation for the moon. So omega on the moon is equal to square root of g, but on the moon, over L. The length of the pendulum doesn't change. If you travel from the Earth to the moon and you take a pendulum with you, this pendulum will not change its length. So this is gravitational acceleration on the moon. It's 1.6 over the length of the pendulum. It's 2.5, and after calculating this, this is the square root of 0.64, and this is 0.8. Of course, I have used a calculator to make all these calculations. Maybe not that, of course, they are quite simple, but it's still much easier to do these calculations using a calculator. Now, the final calculation is for the period. T equals 2 pi over omega. Omega now is 0.8, so it's 2 pi over 0.8. And after calculating this with a calculator, we get the final result, 7.85 seconds. That's the final answer. Now, let's discuss the marking scheme and the most common errors you made. Just for providing the correct formulas, this formula and this formula, you could get 10 points. For the accurate calculation of omega, there was another 10 points. For the correct calculation of the length on the moon, it was another 10 points. For calculating the omega on the moon, it was 10, and for the period, it was 10, altogether 15. More than 50% of you made this task, challenge, very well or nearly well, so there were some minor problems. The main problem that occurred in many cases, and this is, I have to say, a bit disappointing, is with just simple mathematics. So many people, actually too many, starting with this formula, thought that omega equals t over 2 pi, which is absolutely incorrect. It should be 2 pi over t. This is very, very incorrect, and in fact rather unacceptable. So unless you feel absolutely comfortable and confident with this type of transformation, please do some practice before the main test and ensure that you will not do things like this. Okay. Similar error many of you made with this calculation of L, and for many people L was omega square over g. Okay, these are elementary problems, elementary errors that can be very easily avoided. Another problem was calculating the length, which is g over omega square, using the acceleration on the surface of the moon, 1.6, and the omega we have calculated here, this one, over 2. Okay, and this was intended to be a calculation of the length of the pendulum on the moon, But please keep in mind, whatever happened with this pendulum, the pendulum wouldn't change with length. And this calculation here is deeply wrong because you mix up 1.6 is the acceleration at the surface of the moon, and 2 is the omega measured while this pendulum was on the Earth. So you divide something from the moon by something from the Earth. Unfortunately, totally wrong.